All right. Share screen. Whoops. Let me get back this screen first. Okay. And then, so now I can share screen. Okay. Okay. So,
Great. All right. Okay. Welcome everybody to come to our seminar today. We are so honored to have Greta Panova to be our speaker, and she's going to talk about the computational complexity in algebraic combinatorics.
Thank you very much. Thank you for the opportunity to come here. So I'm right now nearby in Princeton, so it's just a short train ride away. Okay, so I'm assuming that you all have different backgrounds, so this talk is gonna be, so it's going to cover things from the basics in some sense, so don't worry about don't worry about any of the details. So it's not meant, not really meant to get into a lot of detail. Okay, so the first thing so this is a combinatoric seminar, but as I said, so people do different things. So I need to tell you what my view of algebraic combinatorics is. And this is not really.
it's not showing.
Now it is. Okay. So first we start with some basic discrete objects. One of them is integer partitions. They're just non-negative sequences of integers which sum up, weakly decreasing, which sum up to a given number. So partition of n. In this case here we have a partition of 5, and we are presented as a stack of boxes. This is what's called a Young diagram. And the next thing we can do in algebraic combinatorics is we can put numbers inside those boxes according to some rules. So for example, in this case, we're going to put the numbers from 1 up to 5, ask them to be strictly increasing along the rows and down the columns. So we have 5 possibilities to arrange those numbers. These are called standard Young tableau. And they are counted, the number of those. There is a very beautiful combinatorial formula. It's the Hooke length formula, which doesn't, the details of what the formula says don't really matter, but it's basically you can see the Young diagram and compute this number very quickly as a product of this Hooke length. So where does this come from, and where does the word algebraic come from? This all comes from representation theory, actually. So if we look at the symmetric group, a group of permutations under composition, so it has order and factorial, of course, but we can also try to represent these permutations as matrices of various sizes, so that these matrices also respect the group laws that they satisfy. So for example, here is one, actually the standard representation of a permutation as a matrix, but there are many other ways we can do this. And then we can consider which ones are irreducible. So you cannot simultaneously diagonalize these matrices into block. You cannot simultaneously reduce these matrices into some separate blocks. Those are the irreducible representations. In this case, this example here, this representation is not irreducible. These two components are fixed subspaces of this representation, and it turns out that the reducible representations of they're classified, they're indexed by these partitions of n lambda, and their basis in some sense, not any direct, unfortunately, are indexed correspond to standard Young tableau. So in particular, this the number of standard Young tableau, this formula that I showed you earlier, is also the dimension of each of these irreducible representations. And of course, now there is a lot of combinatorics you can ask about this using this and use the tableau, try to answer algebraic questions and so on. So there is a dual story to this. This is the general linear group, and so the general linear group is now an infinite group, but we can still talk about representation. So these are matrices, we can represent them as some other matrices, which still respect the group law. And again, we can talk about irreducibles in this case. So this time, these are called Weil modules. They're indexed by what, again, partitions, but here they're called highest weight because the size of these partitions can vary. The only thing that is restricted is the number of parts. And they can be indexed by some generalization of the standard interval, which are the semi-standard interval. So same thing with the Ikenmeyer diagram. We enter the numbers from 1 up to big N, so that they're weakly increasing along rows and strictly down columns. And one way to study representations is through their characters, the traces of these matrices that we map into. And in the case of the general linear group, this irreducible representations, the characters are the Schur functions, and then these have nice various nice formulas. So here is ratio of two determinants, but it's also very combinatorial. It's a general, can be expressed as a positive polynomial with symmetric polynomial with positive coefficients, which each of these monomials corresponds to one of these semi-standard tableau. And so on and so forth. So we can use these types of tools to try to derive various formulas. That's one reason why I'm telling you all this, but also to put it in some comments. Okay, so these are the irreducible representations of Sn and the general linear group. So what next can we do about them? So I guess that looks like it's already pretty well understood. Well, one can take tensor products. Tensor product of two irreducible Weil modules of the general linear group is also a representation, and as a representation is going to decompose into irreducible components. What are those? Well, they could be basically anything, but each of them will show up with some multiplicity. The multiplicity, by definition, is going to be a non-negative integer. And in the case of the general linear group, these are the Littlewood-Richardson coefficients. So they depend on these three partitions. Lambda and mu are in the tensor product, mu is on top. And so they can be computed via characters of the, they also have they can correspond also to representation theory of the symmetry group by restriction to the product of two smaller subgroups. They can be thought of as the structure constant in the product ring for with basis the Schur functions. And they also have nice, what's called a nice combinatorial interpretation. So there is no more Hook-Lang type formula. These numbers are not so nice, but we can still understand by counting something. So this C lambda mu nu is equal, for example, to the number of called Littlewood-Richardson tableau of shape mu over mu and type lambda. So we basically take big shape, outer shape here, you bite off mu from it, you are left with some other squares in a, it's called a skew-Young diagram. You arrange them in weakly increasing order, and there are some more conditions that they need to satisfy. I'm not really gonna go into details, but the point is, you can play around with this. So this one is not so easy if you want to know how many there are. If you want to know if there is at least one, all you need to do is just draw one of these tableaus and check the conditions, which are not so bad. Okay, so that's our like staple or standard for combinatorial interpretation. Why do I say this? So the next thing we can do is we can define the Kronecker coefficients in the same way. Take two irreducible presentations of the symmetric group, take the tensor product, decompose this into irreducible components for the symmetric group. Again, they're gonna show up with some multiplicities. These are the Kronecker coefficients, G lambda mu nu, non-negative integers. You can do them, express them via with sure functions this way. This x times y is the pairwise products of these two variables, so you can extract it as a coefficient in some polynomial expansion. So you could work with this without knowing any representation theory whatsoever, just using these formulas. But so it's not at all obvious this is going to be positive or negative, for example. And then you can do something else. You can compose two irreducible representations of the GLN because they are maps from one GL to another GL to a third one. So you can, if you compose this whole sequence of maps, then you have another presentation, and then you have what's called the plethysm coefficient. So here we have Kronecker and plethysm, some multiplicities, non-negative integers. We can also study those with sure functions. For example, you basically take one sure function and you plug in all the monomials of the other sure functions as variables. That's what the plethysm does. Expand it, and you're gonna get some coefficients. And again, work with this, just using the polynomials. So this is okay. Anyway, so now Morgenagam actually figured out that these Littlewood-Richardson coefficients are special cases of the Kronecker coefficient. So if you take three partitions lambda, mu, and nu such that the size of lambda is equal to the sum of the sizes of mu and nu, and then you add some big parts in front to make three partitions of the same size, so that the Kronecker coefficient they need to have the same size. Then it turns out that the Littlewood-Richardson coefficient is equal to the Kronecker. So Morgenagam actually defined the Kronecker coefficients in 1938 and noticed this property, and then he started asking, so how do we compute those Kronecker coefficients? And in his first paper, he was just trying to do some very, very small examples, and so that it's kind of difficult. So there is no pattern or even methodology for that. And then later on, this problem was taken over by Garcia Remel, and Lascaux, and then Stanley put it as one of the open problems, number 10 in his big list of open positivity problems in algebraic combinatorics, just to find some combinatorial interpretation for this Kronecker coefficient. So are they, I guess there is not gonna be a very nice formula, but are they at least like the Littlewood-Richardson? Are they counting some nice tableau or whatever, some kind of objects? And what are these objects, if this is the case? And so there hasn't been that much progress on that problem. There are only very, very special cases. Probably one of the most general cases of John Blazek, and later with Ricky Leo, when one of the partitions is a hook, so it has one long part and then 1, 1, 1, 1, and the others are arbitrary, there is a way to say that the Kronecker coefficient is counting some type of tableau with two types of letters inside and so on and so forth, but that's the most general, and then everything else is, there are various special cases that show up in various contexts and are one can study those, but measure zero amount of information we have on that level. So why do we care? Of course, I mean, it's a nice open problem. It's very natural. We need to understand this. And of course, the other problem is about this plethysm coefficient the same way. Right? So the same question holds, also was in that survey, and they again, there isn't that much progress on those. Well, again, it's only very special cases. But why do we care? Well, besides the combinatorial and representation theoretic sides, this thing comes in geometry, what's called geometric complexity theory. So this is about distinguishing computational complexity classes. This is a program that is trying to use various symmetries of various polynomials and use algebraic geometry and representation theory to say something of the kind p is not equal to np, but okay, smaller steps at a time. We're not getting there. And in this case, it's going to be arithmetic complexity theory problems, VP versus VNP. If I have time, I can tell you a little bit later about it and how the Kronecker coefficients roll up in this business. So there is one question here, and then the main question that we're going to discuss today is what is actually combinatorial interpretation. So it's an open problem. Usually in an open problem, it's either true or false. So there should be a way to disprove it if it's not true. But with that kind of vague description here, there is no room for it. So we can always say, okay, combinatorial interpretation, well, it's counting the subspaces of whatever. I mean, that's not, but it's not actually useful. So how do we define combinatorial interpretation? And this is where this computational complexity now comes in. Okay, so we're now going to switch to computational complexity a little bit. Any questions so far? All right. So, no, I'm not gonna, normally that computational complexity is defined with Turing machines, and just to define a Turing machine, it takes some time and all that. It really doesn't matter for us. You can think of a Turing machine as your computer or your phone, whatever device that you can program in and give it a set of instructions and get some answer. And there are various decision problems, and of course, so we're doing deterministic computation. So no quantum computer here, just a regular computer. So there are various classes of problems depending on, well, how much time or space they take in order to solve them, the like optimal time and space. And in general, so the decision problems are when you have some input and you want to know something about this input, which is in the form of yes or no answer. So you get an integer, you give it to the computer, you want to know if it's prime. That's a yes or no answer. That's a decision problem. So you put it in the computer and you have some algorithm, some program that's gonna take this integer, do various computations on it, and in the end figure it out and spill out an answer. So there is a way we want to encode how long these things take, and there is a parameter here. The parameter is the size of our input. So if we put in an integer, usually it's encoded in binary, how many bits it takes, let's say n bits, then the input size is gonna be n, which means that the integer is no larger than 2 to the n. So if we do binary. So there is some notion of an input size, And now we are going to care about how long, if we give input size 10 bits, how long does this algorithm take? The most optimal, the fastest way possible there is to compute this, how long is it gonna take? And so now we're define these classes. The class P is when we get an answer in polynomial time, polynomially many operations. N to the k, where k is some fixed number, n is our input size and is the parameter here. And regardless of which integer of n bits we put in, it's always gonna take at most n to the k operations. So that would be in the class P. And in fact, checking if a number is prime is in this class, and that was a breakthrough paper. It's not obvious at all that it is going to take polynomial amount of time to check if a number is prime, but let's say you want to check if a graph is connected, that's also going to take polynomial time. Or you want to know if a system of linear equations has a solution, a real solution, let's say, not integer solution, so that's a different problem. That's going to take polynomial. And then there is the class NP, where it's, so the definition is a bit tricky. Probably, well, we're kind of assuming that the number of computations we need to do to figure out the answer is going to be exponential, but if the answer is yes, then we can check it within polynomial time that this is indeed true. And so let me give you an example of such problem. We want to, given a graph, let's say encoded via its adjacency matrix or something like that, want to know whether it has a Hamiltonian cycle, whether you can go along through every vertex exactly once by following edges. So there are no known polynomial time algorithms so far. That the best algorithms are going to take exponential amount of time to go. And the stupid one is just go over every permutation of vertices and check them one by one if it forms a Hamiltonian cycle. That's already a factorial is exponential. But if the answer is yes, all you need to do is give me that Hamiltonian cycle, so that sequence of vertices, and I can check. And actually, in time n, the number of vertices, whether this is actually forming a cycle. So there is a way to prove. And of course, so we kind of believe that P is not equal to NP, but we don't know yet, so that's a big problem. And so P and NP are just small, two examples of a big zoo of the complexity zoo. And actually, if you go to Wikipedia, there are a lot more letters involved. So there are a lot of complexity classes that we don't know. We have various containments between them, but we don't actually know exactly which one coincide with which, but they are actually formally defined entities that we can work with. And then there is the analog are the counting problems, where you, given some input, for example, that graph that I mentioned earlier, you want to know how many Hamiltonian cycles it has. So you want to know a number. And then there are the two classes FP, where you get the answer in polynomial time. And then there is this Sharpie class, which is the counting analog of this NP. It's basically the answer is going to be sum over exponentially many things. So this is why here is some parameter space of exponentially many options. But each of these things that you're counting takes polynomial time to verify. So you're counting, you're going over exponentially many objects, but you check in polynomial time if each of these objects is the thing you want to count. So there are things that look whose sum looks like this. And again, this is like a more explicitly defined type of counting function. So at least you know what you need to, how your formula should look like. So you have a lot of freedom here. The only thing is that this thing needs to be positive, no negative, and you need to check here for time. So what does this have to do with combinatorial interpretation? Well, the philosophy is the following. So if we have a nice formula like the one I showed in the beginning, then the decision problem is in P and counting problem is in FP. So things are easy. It's like Cook formula, determinant is easy also, things like that. And it's in the classes. If you have a positive combinatorial interpretation like the Littlewood-Richardson, so you're counting some objects. In each of those objects, you can verify easily that it's one of the guys that you want. Then it's basically by definition what I showed just now is a problem in Sharpie. Exponential large sum of things that you can verify. So then if there is no combinatorial interpretation, the problem not in Sharpie. And if the problem is not in Sharpie, then there is nothing good that's gonna, there is no nice positive formula that's gonna show. And so this is how we want to, what we want to use as formalism to say that something does not have a nice positive combinatorial interpretation. The Sharpie class is actually pretty large. And even things that are in it are probably not what you want in terms of combinatorial interpretation. But if it's not here, then, then you really don't want to deal with this. Okay, so let's just do some warm-up with things that I mentioned in the algebraic combinatorics. Say we want to count the number of standard Young tableau. Now, so everything is defined in terms of this input size. So what's the input? The input, in this case, is going to be the partition lambda as a Young diagram. So you can imagine that I just mark some, like a matrix, I mark some boxes in the matrix, that's going to be the input. And there is a reason to do it this way, because otherwise the answer would be over exponential, so we wouldn't even be able to record it in polynomial times. And then, so that's what's called inputting unary. Basically, the input size is the number of boxes in this, for our purposes. And then, of course, the formula is this one. How many computations gonna take? Well, about n, let's say. Or 2 and 3 and whatever, whichever way you want to, however you want to implement. So the problem is counting the number of standard Young tableau. So skew semi-standard Young tableau, for example, that showed up earlier, how many of those are there? There is no more Cook length formula, but there is a determinantal formula. So in this case, we're not going to specify the type, so this is not a Kostka number yet. So, but we have a determinantal formula, which looks like this. Again, we can compute it in polynomial time. So this is in FP. So here are the Littlewood-Richardson numbers with the combinatorial interpretation. So what can we say about them? So we can ask about their positivity, and we can ask about their computational complexity. And the actual number. And so it actually turns out that, so deciding positivity automatically is in NP, just because if it is actually positive, then all you need to do is just write one of these tableaux. But it turns out it's even better than that. It's actually in P. And this is due to the Knudsen-Tau saturation theorem, that it showed that if the Littlewood-Richardson coefficient is positive, then certain polytope is non-empty. And if you just want to know if a polytope is non-empty, this is just linear algebra that you can do in polynomial. And it's a little bit of a miracle in this case. So the Littlewood-Richardson coefficients are very special. So what about computing the value? And here is a tricky part. If you actually input your partitions in binary, in the sense that lambda1 is encoded in binary, lambda2 is encoded in binary, and so on. So your input size is this big. So log lambda1 bits is gonna take to encode the first part, and then let's say upper bound to the length of the partition. So your input size is kind of small compared to the actual partitions. Then the problem is actually Sharpie complete by a result of Narayan. And so, yeah, so input size here matters. So what happens if the input size is in unary? You just give the Young diagram. We don't know actually where. I mean, it is obviously in Sharpie, so it's counting those objects. There are exponentially many of those, and each one of them you can check in polynomial time if it's your tableau. And we conjecture that it's also Sharpie complete, but there are no tools, and this is actually related to a much more general problem about counting graphs with given degree sequence. And we don't know even that one where exactly it lies. So since it's like a major thing in computer science, it may not be. So it's certainly not so easy, but it may not be actually, sure. So it might be somewhere in between. So there are other classes between FP and Sharpie and so on. So it's not exactly clear where it is. Okay, so now about Kronecker that I just mentioned. So the whole framework here is built around understanding Kronecker. So first of all, Mulmuri, who was actually the father of this geometric complexity theory, the Kronecker coefficients were showing up in the various computations he needed to do. And he was kind of wishfully, in analogy with Littlewood-Richardson, he said, oh, then Kronecker positivity is gonna be in P. Gonna be as nice as Littlewood-Richardson, and actually later he disproves himself. That is actually NP hard. So that's, if we assume P is not equal to NP, which we probably should, then this is strictly worse than Littlewood-Richardson. That's what it means. But we don't know if it is in NP, in the sense that we don't have, if it's positive, we don't have an object to prove that it's actually positive. So then he went further to conjecture that it is going to be in NP, and then there is going to be a combinatorial formula that would put the Kronecker problem in Sharpie. And we should say that the Kroneckers already we can write as the difference of two things that are in Sharpie. So two positive exponential sums of various nice objects, but the cancellation of the terms in the difference is totally not clear how it's going to happen. And in that sense, kind of this is the closest class you can think of when you consider this fact. And then my collaborator Igor then he went the opposite direction and he conjectured that the Kronecker is not in Sharpie under, of course, some complexity theoretic assumptions, because we're not really going to prove P is not equal to NP. And then there wouldn't be a combinatorial interpretation. And the same thing holds, basically the same type of results and conjectures hold for the plethysm coefficients. So they are NP hard, and so and therefore the computing them is also going to be Sharpie hard, and it's it's about on the same level of problem as the Kronecker. So if you conjecture Kronecker is not in sharp P, these are probably also not in sharp P. And okay, so these are all open problems in some sense. So what can you actually do? So is there something that's not in sharp P that makes sense? So, okay, so now let me give you a proof of concept that this thing actually might work. I'm not gonna prove Kronecker today, but so let's take something even more basic than any of that. Take the characters of the symmetric group. So if you study any representation theory, you compute character tables, and if you notice, so a lot of times the entries in the character tables are irrational, complex numbers, blah, blah, blah. But if you take the symmetric group, then they are gonna be integers, right? And in fact, there is some kind of way to compute them combinatorially, but it's a big sign sum, right? So plus thing, minus thing of objects that look like this. These are monogamic tableau. And in an algebra class, you'd never do this because it takes too much time. So you usually in an algebra class, you're gonna do orthogonality of rows and columns and try to find the actual representations and so on. But so here is the keyword. So it's a sign sum, and the question is, can we cancel those signs somehow? So we are left with only a positive or negative things, because this can also be negative. And of course, the characters show up everywhere, including in Kronecker. So we understand those, we can probably understand Kronecker better as well. So here is the character table of S4. Which you may have computed with this Murnaghan-Nakayama rule, but it's easier to do otherwise. And so what's the first column here? This is the valuation of the identity permutation, which is just the dimension of the representation. So if this F lambda, the hook length formula that we have, this is the first column. And we have this identity, which actually holds for every finite group. The sum over this dimension square is equal to the order of the group. What are these things? These are pairs of same shape standard Young tableau, right? And if further is this RSK algorithm, which assigns to each of these permutations counted by n factorial a pair of standard Young tableau. And so this identity here is very combinatorial, so that a lot of things are done around. So now you can take another column of the character table, for example, this one, and and the formula, the general formula is that the sum of this character squared is, well, this kn factorial over the size of the conjugacy class, and which is just this product formula. So the C's are just the number of cycles of length corresponding permutations. So again, you have some nice product formula here. Do these things mean something? So the character square, these are gonna be integers, square integers, in fact. So are they actually counting something? Does this have any combinatorial meaning? Or you can phrase this in terms of combinatorial, in terms of computational complexity. If you have character square, what is this counting? And unfortunately, then the character squared is not actually in sharp P, unless the polynomial hierarchy collapses to the second level, which is another, basically the next, so P not equal to NP, and then there is a next level of the next level in these types of iterations. So and most people assume that all this levels in the polynomial hierarchy are different, just like p is not equal to anything. And so there would not be a combinatorial interpretation for these numbers. Don't give this to the students. Yeah. So of course, people always object, but what if you take whatever the second column or something? Yes. So in some cases there are, but the general case is not gonna be. Not gonna be good. So how do we do this? How do we show something's not in sharp P? So we need to find various reductions. That's how usually things work in computational complexity, to reduce to some known hard problems. And we're gonna start with this, what's called ordered set partitions. So we have two sets of integers, A's, which we call items, and B, which we call bin sizes. And we want to split those A's into groups so that the sum in each group is equal to the corresponding B. So it's like, and they are ordered, meaning that these are treated as different depending on where they are. And so here I have one. So here is an example where I've colored all of these A's. So there are 5 different ones, 2 different 2s, and 1 3. And we want to split them into bins of sizes 4, 4, and 4. One way to do it is we can take this one and this one and this 2. We get a 4. This one, this green, the blue 1 plus the 3, and so on and so forth. And there are many more ways to do this. In this case, I computed this is 245 ways of splitting these numbers into bins. So this is some generalization of Stirling numbers. But parts are parameterized with those A's and B's. And what it turns out is that, so I showed you Murnaghan-Nakayama rule, but actually there is a different formula for the characters you can write, which is kind of similar to, Jacobi-Trudi identity. So the character of irreducible representation lambda evaluated at a partition alpha, or this is the class, the type of the class type is sum over some permutations Sk. So this is just the number of parts in lambda here. And then we are partitioning these alphas into bins of size this. So ID is the good identity permutation. So that's another way to compute characters. It's different from the Murnaghan-Nakayama formula. It's not necessarily any better, but it's a more compact way to write it, and also to use this function here that we have. And now we kind of, so this is a big sign sum. We don't know really what to do when we have something like that. So we are just going to take specific types of lambda and alpha. So we're going to use some prime numbers and so on, just so we can kill most of those terms will become 0 when we do that. And in the end, we can start with 2 arbitrary sequences of non-negative integers, which have satisfied this restriction. And then we can find lambda and alpha that are not much bigger than that, such that the character is just the difference of these 2 set partition functions. So they're the same items, but the bin sizes are just different by this. Like one has 2, 4 something, one has 1, 5, and something. So it's difference of 2 set partition functions. And now the set partitions is actually a hard problem, a sharp P complete problem. And now we go back to see how one proves that this is sharp P complete in order to separate these things and make them independent. And this goes back to, it's called the 3D matching. Not gonna go into the details of how this works, but basically 3D matchings look like this. You have some hypergraphs where the edges are just triples of vertices. And in this case, these are regular, so you have 3 columns of vertices. Each hyperedge has one of these 3. And you want to count the number of perfect matchings, which in this case is going to be like sets of size 3. Each of them covers exactly 1 vertex. So we'll just work with the normal perfect matching. So we have 2 independent 3D matching problems here and here. We can put them together as a 1 4D matching problem where you know exactly in which, by this wedge in the beginning, basically depending on which direction you choose for the one of these yellow vertices, you know in which matching you're gonna go. And there is a way to encode picture like this in terms of a set partition function. And I wrote this down just to scare people how encoding works, but there's a big branch of combinatorics coding theory, and then it uses notions like this. So perfect matchings correspond to various set partition problems where we encode our edges and vertices in terms of just various numbers, actually. And then a perfect matching would give you that these numbers add up to, well, they form a bin of some kind. So how do we use this problem? So the character is proportional to the difference of these 2 things. And now I told you these are basically independent. I started with this 3D matching and I made it look like this C and D partitions, and then there is a lambda and alpha. So this is our polynomial hierarchy, which I stole from Wikipedia. There is the class P, there is the class NP, and then you can use each one of these classes as a machine and then take it in augmentation to another Turing machine. So you can actually build a tower of classes where you can do more and more things using this. This is the polynomial hierarchy. And then the second level is, so there is this thing here. This is like the second level. So we assume, and people assume that all of these are going to be different. So here is our statement from before. The character is proportional to the difference of this 3D matching. So if I want to know whether the character is 0, this corresponds to saying whether the number of 3D matchings of some graph is equal to the number of 3D matching of another graph. And these 3D matchings are generic functions that encompass all of this sharp P. They're sharp P complete. So this is what's called a gap P complete problem. So just the equivalence of 2 sharp P functions being equal. And then if this was the character squared, for example, was in sharp P, then it means that deciding positivity is going to be in NP. You just take one of these positive entries that it's counting in the sharp P formula. So deciding whether character is non-zero is in NP, and so I didn't define this, but there is this class co-NP, which by definition is exactly this. So non-zero is in NP, then 0 is in co-NP. The complement of NP. And then since this is C equal P complete, then it will have to be inside this class co-NP, and then you write the various implications, use some CS theory to say that if this all happens, then the polynomial hierarchy would collapse, so it wouldn't work. And so there is no nice combinatorial interpretation for our character square. So no, do I have more? We need to finish with it.
No, we still have like 10 minutes.
Okay. Okay, so that's about Sharpie, and that I can tell you in 5 minutes what the geometric complexity theory was and how this Kronecker coefficients show up there and what this has to do with anything. So this is so far was application of computational complexity to answer combinatorial questions. So let's go the other way. So in arithmetic complexity theory, we are maybe it's actually easier to define than the Boolean complexity that we started with earlier. We're just computing formal polynomials, like you would do in Mathematica or Sage or any of these symbolic computation systems. So you have constants that we are not gonna care about at the moment, what their size are from some field, variables, and then you wanna spit out some polynomial, and what's the model of computation? In this case, I've drawn what's called a circuit, where it's like a directed graph. At every vertex, you have a bunch of inputs, but there is, and then the output is passed on to some other nodes afterwards, and this the vertex, the intermediate vertices are just some simple operations, plus multiplication, minus and division, and then you can of course multiply by various constants along the way. They also come in as inputs. And then in the end, you get your polynomial out of one of these vertices. These are our gates. So again, so there is pictures like this, have complexity measure. What's the measure? How many nodes do we need in order to compute our polynomial? So in this case, we are computing polynomials, and we want to know what's the optimal number of simple operations we can do to get our polynomial out. So in this case, we needed 3 gates to do this polynomial, and but we could have done with 2 actually, because these factors. So if the polynomial has n variables, then we are going to also assume that the degree of the polynomial is not really larger than the number of variables. So and for those polynomials, there is the class VP where you can compute it with polynomially many nodes. So n to the k many nodes of this type. And then there is the class VNP, which is basically like an analog of NP or Sharpie, actually more than like the class of polynomials, which are exponential sums of things that are easy to compute. And so, of course, so what's the connection with P versus NP? It's not very obvious, but if VP is equal to VNP and you prove it over a finite field, then P is gonna be equal to NP. Or if you prove it over C, but the general Riemann hypothesis holds, then also P is gonna be equal to NP. So that's too much, too many conditions. But but in the other direction, though, it's not quite clear. So if VP is not equal to VNP, you can't really say that P is not equal to NP. So it's a little bit weaker statement. But again, we believe that VP is not equal to VNP, and this is still one major open problem. So how do we treat this? And so as with any other complexity theoretic problem, you have kind of like complete problems, and you want to show that complete problem is not in the smaller class, and that would separate them. And what are the problems in this algebraic complexity? There are two polynomials in particular we want to distinguish: permanent and determinant. So here is the naive definition of a determinant. We have an n by n variable matrix. It's assigned some over permutations. And the permanent is the same thing, except there is no sign anymore. And there is a whole family of immanents. You can put whatever character representation you want here, but things only become worse. And so this turns out that determinant is universal for VP and permanent is universal for VNP in some sense. So permanent is actually hard to compute, determinant is easy. And not only that, but every polynomial that is in VP, it can be computed as a determinant of some polynomially sized matrix with fine linear entries. So the determinant itself is like a computational model which you can use to measure your complexity. And so if you want to prove that VP is not equal to VNP, then you need to show that the permanent cannot be expressed as a polynomially large determinant with the fine linear entries, which now becomes an algebraic statement. And now these two polynomials have a lot of symmetry, so you can act with general linear group on the entries and take the whole orbit closure of those polynomials you are getting. And so if this thing holds, then these orbit closures would be contained like this. What they are, we don't really want to. It's not exactly your friend, but it's now these are actually algebraic varieties, and you can talk about use algebraic geometry to study them. And basically, it boils down to showing that take the coordinate rings of the orbit closures, those are actually modules of the general linear group. They can be decomposed into irreducibles, and now you want to compare them. All you need to do is find some irreducible representation which shows with a smaller multiplicity in one versus the other, then you have no containment possible. And those representations are called abstractions. So if you find some lambda with this inequality for n bigger than poly m, then you get VP is not equal to VNP. But those multiplicities are difficult, as you can probably guess. So then they were hoping that there is a current abstraction, that when this is 0, the other one can be positive for n super polynomial in M. And turned out this is not the case. So this never happens. So there are no occurrence abstraction, and at least this strategy is not gonna work. And how do we prove this? Basically, the brief story is that these are related to Kronecker and plethysm coefficients, these multiplicities. And you can use tools that, even though we don't have formulas for Kronecker and plethysm, we still know a lot of properties that we can understand. And it turns out that Kronecker coefficients are always positive when you don't want them to. And actually bigger than the plethysm coefficients, as we showed subsequently. But so first of all, those are positive, and then you can also go to the level of this delta, which is not so far from the Kronecker coefficient, and show that it's also positive whenever this gamma is positive, and that's basically how things work. And that's it.
Thank you so much, Greta. Any questions for the speaker?
It's all difficult.
But it's like, it sounds like even Kronecker coefficient is hard to compute. You can still use it to tell other people and other things are hard.
Yeah,
It's like, it's not like completely
so it's a
useless.
lot of negative results you can still do. Yeah.
But is it like, my question actually is that like, if I see a problem and I don't know whether it is like worth doing or not, like how do I even, like say for example, now you can say, okay, well, this one is not possible, so don't give
Yeah.
it to your student. But
Yeah.
in general, how do I even think about
So in general, at least, I mean, in practical terms, you try to understand your problem for various types of parameterization, so it's special cases, but like families of cases. And then you need to find another hard problem that shows up from them. And so for the characters, you start writing that you see there you have this set partition problem, and that set partition problem is already hard. So, and now you have an alternating sum of those, so it's probably not gonna work.
I see.
And I mean, for Kronecker, there are also things like that that I didn't really mention, but it's, I mean, now the hard part is to single out the hard problems in a nice way to show that this is not going to work out, because right now it's a lot too many of those and they still might cancel. But that's one way, is to try to write your problem for some families and see if something actually known and difficult shows up, let's say, or Hamiltonian cycles in a graph, or I don't know. Yeah. And the set partition problem actually shows up in combinatorics, the algebraic combinatorics quite often. So if you see that, then yes. Yeah.
Yeah, I mean, I mean, I may be a little out of the box, but you know, like so in physics, you know, like particle systems, like it is a big problem, like simulating, you know, like terminals, like and then the main abstraction is the solo sign one. It all boils down to the difference between permanent and the terminal.
Ah.
Is there any connection between that and PP and EMP, or?
There may be, but I'm probably not the right person to ask, but it sounds more like the operator scaling type of polynomial identity testing would go in that direction, because permanent versus determinant can be also studied with those methods, but yeah, so in like practical terms and statistical mechanics, you have fermion point is nice, and boson point is somehow difficult. But those parts we haven't formalized yet, simply because you need enough parameters to make sense of it complexity wise. So that's another problem.
Any question? Let's spend the speaker again. Thank you so much, Greta. Yes.